A graphical model, or so-called belief network, is essentially a tool for expressing your knowledge about these kind of distributions. So it's a graphical way of expressing how random variables interact with each other. And the graphical way is really just a tool for us people in order to understand and handle these kind of expressions, knowing what we're allowed to do and what we're not allowed to do. So this is the typical notation of a belief network, also called the Bayesian network. It's a directed graph, and each random variable is a circle, or it's a node in the graph, and they are connected with arrows. And so in this case, this is the rain, this is the sprinkler, and they're both connected to homes. And sometimes when we say, okay, what's happening when we observe that a certain variable has a certain value, we use the convention that we shade that node. So once we observe that home's grass is wet, we would communicate that to the world by saying, okay, this is the random variables, but this one is actually observed, it's 1. And again, if we observe more, then this one would also be shaded, and so on. So the nodes in the graph are the variables, and the arrows, they specify some form of conditional dependence that we started with, and the exact form of that will come in like a few minutes. So what this thing actually does is it provides us a way to write the conditional, the probability table in a compact way. So the definition would be such a network specifies a probability distribution, and it's not any distribution, it's only a distribution that can be written in a very specific form, like we did before. It has to be a product, and it has to be a product of conditional probabilities, the probability of one variable at a time, conditioned on all its parents in the graph. So here this specifies a conditional probability, sorry, not a conditional, just a joint probability of 4 objects. And we know from this graph that we can write this probability in the following way. It's the probability of all the variables, so n, for example, and it's the probability of n conditioned on the parents of n, so n conditioned on r, multiplied with the condition of probability of r conditioned on its parents. It doesn't have any parents, so just the probability of r, multiplied with the probability of h conditioned on r and s, and multiplied with the probability of s. This is what the graph tells us. So the moment you see this graph, you know that this kind of factorization is true. It's important that there's no cycles. So this only is defined for directed acyclic graphs. No cycles, and directed graphs. Okay. This, of course, is exactly the representation we had before, right? So where is it? H had to be conditioned on R and S, N had to be conditioned on R and S had to be conditioned on nothing. That's exactly the arrows you see here. H conditioned on R and S, N conditioned on R and S conditioned on nothing. Okay? So instead of all this derivation of sprinklers, I could have just given you this picture, and then you immediately would have known how the distribution factorizes. Okay, that's the graphical notation we're going to use. There's a large number of very, very useful of these belief networks or Bayesian networks out there that do surprisingly useful things. And they are kind of quite useful because they're really close to our intuition of how modeling things. So for homes, we knew that the sprinkler should not depend on the rain. The rain should not depend on if somebody switches on the sprinkler or not. Right? So this is something it's prior knowledge, we can easily put it in, and it directly corresponds to some kind of graphical structure. So here's another one that makes a lot of sense. It's a hidden Markov model. We have 2 times t variables. T is some number, I don't know, 10. And they are arranged in the following way. We have one row here of h's. We have one row here of x's. The h's have a connection from left to right. The x's are connected to some h with an arrow from above. And typically these things emerge in a place where you want to model some kind of temporal process. For example, a moving object. So the h could be a random variable that specifies where is a certain object at a certain time. So, I don't know, a 3-dimensional coordinate in space or something like that. The x is an observation we make from that, maybe a radar image or something, or a sonar, or a camera image or something like that. So the X's are observable radar signals, the H's are maybe what we care about really, which is where the object is. So the network structure clearly shows you how these things interact. So the observation at a certain point of time, well, light is very fast, so it only depends on the position of the object at that time. So the X variable at a time t equals 2 only is directly dependent on the H variable at the time 2. The positions, well, the object moves around, so the modeling assumption here is that the next position of the object, well, it depends on the previous position of the object. That makes kind of sense. So maybe it's flying at a constant speed, so you always have a certain offset from the previous, and this is encoded with these horizontal arrows. The position of the object does not directly depend on what I observe, right? So it's not that there's like a direct connection from the position I measure at a certain time to the signal I observe to some position later or so. There's also no backwards arrow, which would mean the position, what I measure now depends on the future, not likely, right? So this is a very intuitive model, and it allows you to answer all kind of questions. In fact, this is the model which people used for, since the 50s in order to find out where objects are when you only have a radar signal. So, if you know Kalman filters, basically this is a Kalman filter. I mean, you can put a Kalman filter into this framework. So one question is, well, what is the trajectory of the object based on the observations, right? I observe time series down here, but what is the really distribution of the H's? It would be a conditional distribution, all the H's 1 to t conditioned on the observations x1 to xt that we made. You can also ask, I observed x1, x2, x3, what's the most likely next position, right? So not the trajectory, but predicting where the object is going to be in 5 minutes. Maybe you want to shoot a missile at it or something, right? So all of this comes out of just modeling this probability and computing the right marginal or conditional distributions. Here's a model that is very popular if you work with text documents, and it's remarkably simple if you draw it as a graphical model or a belief network in this case. So it's a so-called generative model of text documents, the bag of words model. You have one variable that tells you which document you're talking about. It might be, I don't know, a file name or just the ID of the document in your database. And then you have a lot of variables, each of which tells you which word it is. So this is the first word, this is the second word. Clearly, the first word, the second word, and so on can be, I don't know, whatever words somebody put there. So it's a random variable that can take as value any word. And then, well, that's already it, right? So a document is just a sequence of words from the first to the end. By drawing it in this way, we impose a certain structure on what we use, or how we think about this as a generative process. How is a document created? Well, in this case, it's a very simple model of how to generate a document. So the distribution of a whole document, if you remember, how does the distribution of this guy look like? It has to be a product. It has to be a product over the individual variables conditioned on the parents. Right? So this guy, the probability is the probability of the first word, or of the document ID, which doesn't have a parent, multiplied with the probability of the first word conditioned on the document, the second word conditioned on the document, up to the last word conditioned on the document. So this means we can relatively easily construct documents that follow this model. So we just, yes?
Why aren't the words connected? Because the second word is dependent on the first word.
Yes. So yes, we could do a different model where these would be connected. That is true. And that would be a way better model of language. This happens to be the first model that people used in order to model text. And it's a model where there is no direct connection. So in fact, well, we didn't talk about independence yet, but this will be a model where the words at this location are actually independent of each other once you know which document you're in. Which clearly, as we saw before in the English example, is a horrible model of language. It's just also a very simple one, and it turns out that it works in some cases surprisingly well. So this is not a true generating process for a language. It's just a model we can impose and see, okay, how do documents look if we assume this model? So how would they look? We need to fix one of these values for the document. So we sample a random value, a random document ID, I don't know, 5. And then we get values for all of these, which are okay, so the process for generating a document from this thing would be, first you choose your document ID from all possible ones, and then for each of these arrows, you randomly choose a word according to the distribution, and that would have given you a random instance of a text document. So it's a word according to the distribution of words in that document. Each document has its own preferred words. Some documents talk about these words, some documents talk about other words, but that's the only thing that we impose. Some words are more likely in this document than others. Extremely simple model, surprising that it's actually useful for certain things. It's not useful because you would get actual good documents if you make this process. They will be gibberish. But if you compute the probability under this model of certain documents, you will see that they can be useful for making decisions. For example, spam classification. Sorry? Sentiment analysis. A lot of simple classification tasks for text, for example, you can use this model and get very, very far with very little effort. Okay. I included this because it's an example of a so-called generative model. That means it's a model where you can create instances of data by a sampling process that you can read off from the model relatively quickly. You have a joint distribution of document ID and all the words, right? Because that's what this graph specifies. And you can create instances of these kind of assignments by randomly following this kind of procedure. As I said, it's not going to be a very interesting text. But yes. I mean, we're on slide 14, so yes. So far, I mean, we only saw 2, right? We saw this one, and we saw that one. So the homes, and these are all generative models, so we can just, create data that way, because we have a joint distribution of data, and we know how to, what the distributions of each thing is. Yes, that's true. Okay. Here's a slightly better example of a generative model, and it's a so-called topic model that was built as an extension of the previous model. And you can see that the graph gets a bit more interesting. So what people did is, instead of directly having the document the word be generated from the document ID, they introduced another intermediate variable, which they called a topic variable. So this is a variable that can take some kind of discrete number from, 1 to k, maybe 10. And now, instead of creating words directly for each document one after the other, you say, well, from the document, in order to create the first word, I choose a topic, and from this topic, I choose a word. There's no connection between the words. It's this graph. So if you write it as a giant probability, it will be a product over the probability of the d. The z's have a product of z given d, and a product of each word conditioned on the corresponding variable of the topic. Yes.
Is it true that each topic has several words or only one?
No. Each topic, the word is sampled according to so the probability of the word, the joint probability of everything, contains a term that says probability of a certain word given the topic. So every topic has a certain, all words can happen with different probabilities. But how likely a certain word is chosen depends on which topic was chosen. We'll see an example in a second. So this is a generative model where you would start sampling first this variable and then the word corresponding on that. And depending on which value these have, you can get different distributions of words. One topic has these kind of words preferable, the other has that one. Admittedly, this is a bit abstract, so let's look at some example, because these were used for real kind of text analysis. But before we do that, let's simplify notation a bit. So this was one document, right? We have one document ID variable that has many words. Now, if you want to do this for a whole corpus of all documents that you've seen in your database, well, you need a lot of these models, right? Each of them is one document, and that is a bit of a nuisance to write. So people came up with a better way of writing these things, and that's the so-called plate notation. So plate notation means you put a box around the variables that you have, and you write how many copies of them you want. So instead of writing this kind of thing n times with little dots, we just say, okay, there's one D, but then there's n copies of Z's that point to W's. So this is the compact version of writing that guy. Okay? And then instead of writing all of these models n times, well, we just put another plate around it. We say, well, now if we have a corpus of m documents, each of them is modeled by this model, so we just have m copies of this individual model. And for laziness, we assume that all of them have the same number of words, namely n, but of course we could change the number of words if we really wanted to separately. So this is a very compact notation for that mess of arrows and vertices. And in fact, this is a very popular, famous model. It's called probabilistic latent semantic analysis. Was introduced in 2000, roughly, for analyzing, more or less getting information out of text corpora, what people talk about.
Here we have m topics and m documents.
Sorry?
M topics and m documents.
We have m documents, yes, because the document variable is m times. And then for each of them, so for each of that part inside, we have n words, where each word has a topic variable and the corresponding word variable. Yes. So overall, we have n times m of these, n times m of those, m times those. Sorry, hard to pronounce. Okay, now some examples. What this gives you is a giant joint distribution over all possible words, all possible topics, and all possible document IDs. Now, the document IDs are not so interesting. They're just whatever your database tells you. But topics and words can be interesting. So imagine you have, so a topic, as I said, is just a number between 1 and k. So turns out when you train these models on real text and let the stuff rearrange its probabilities in the right way, you get something like this. So each topic, 1, 2, 3, 4, has a distribution over words, right? That's how the stuff was generated. For each fixed topic, you have a distribution which words are which likely, how likely. When you look at which words are most likely for a certain topic, you got stuff like this. So in topic 1, these were the most likely words after you trained it on some English corpus. For topic 2, these were the most likely words. For topic 3, these were the most likely words. For topic 4, these were the most likely words. So people immediately sat down and said, well, these are not random, right? There's some structure. The model has learned to identify that certain words co-occur together. And what it did, it put stuff that has to do with, I don't know, culture into the first column, stuff that has to do with money in the second, stuff that has to do with family in the third one, and so on. So people thought about, well, it has identified that people tend to talk about certain words together. Yes?
I'm afraid that these lists are filtered on some common words, yeah? Like article.
I think stop words are removed, yes. So the word the and, I mean, some really frequent ones that have no meaning, yes. But these are the ones that actually, I mean, yeah, that was nouns, I guess. They're all nouns, right? So these are just nouns. So people, these are easy to interpret into arts, money, children, education, and so on. So they came up with the idea that people don't put words together randomly, as in the bag of words, but they choose words based on some topic, because every document has some kind of topic. Right? Of course, there was more than 4. You can look up, there's like 50 different topics that they learned, and many of them make sense. And now you can ask the other question, so given that you're in a certain document and that you have a certain word position, what's the topic? What's the most likely topic? Again, that's just the conditional distribution that we can compute from our big joint distribution. And people color it, I mean, just for illustration, they colored each word in this text by which document, which topic is the most likely one where it came from. And you can see that it makes sense. So apparently they talk about children and budgets. Well, it's a bad example because all colors occur. There could have been much more topics, of course, which would be sports and military and I don't know what. And these would not show up here because most likely this is a document about children, education, and money. It's not a document about sports. So people use this kind of things to analyze documents for what is the content, what are they actually talking about in this document fully automatically. That's not the end of the story. So after LDA became popular, people noticed that it's not that flexible because you really need to know in advance what your documents are. So you have one fixed document variable, which tells you it's document 5, it's document 7. But there's no way if you would get ever a document 99, well, it doesn't include information about that at all. So it's not a way to reason about new documents or to infer anything about the future. It's just for this fixed corpus. So they came up with an extension or a new version which was called Latent Distribution Allocation, LDA, which is a more fancy version of the previous. So they still have this kind of plate, so there is still M documents, and each of the documents has M words. But now instead of a document ID, you introduce a variable that tells you what is the distribution over topics. So each document has a certain topic distribution. This document talks about sports with 90% and 10% about money. This document talks about politics with 50% and 50% about children, this kind of stuff. So each document has some kind of distribution of that kind, which is called theta here. And then these are influenced by external parameters as well. So they introduced parameters alpha and beta, which will be able to, if you have a new document, you can take the outside and create one of these by sampling, and so on and so on. So LDA is a more fancy version of the previous, but in the graph, it's just a few more extra nodes, and so on. Clearly, that was not enough. So the next thing they came up with is a so-called author-topic model. Well, not the next thing. People came up with a lot of models, but this is one where the reasoning was not just, well, each document has a certain topic, or many topics, but it also has different authors, right? So if you write a paper together, some report, then some authors have a preference for some words and others have a preference for other words. Some people misspell, I keep misspelling the word privileged, I don't know why. So that would be something that I do in the part I write, but somebody else would spell it correctly. So clearly there's a different distribution going on. Right? So they introduced more variables. So let's say there's k different authors, and each of these authors has its own distribution about topics and words. Oh, no, sorry. This is still the document topics of distribution of topics, but then each author has a distribution of words. So to choose a word, you have to not just know what the topic is, but also who the author is. Right? That in the end gives you a distribution, a joint distribution over everything: words, topics, authors, document. I think that's it. Again, once you have the joint distribution, everything else is just computing some probabilities. So given a new text document, you will now be able to say who most likely wrote this sentence, or what's the probability that this part is about politics, and so on and so on. So a giant joint distribution helps you to answer these kind of questions if you can write it. If you would try to write this model with all the arrows and boxes and so on individually, you would get crazy. But in this plate notation, it's not so bad. I mean, it's still pretty bad, but it's not that bad. Okay. Enough examples about text. Let's go back to how we actually write and why we write these models. So I said that the joint distribution had to be written as a product, and it has to be written as a product over all distributions and all variables conditioned on the state of their parents. Right? That's the rule how a belief network has to look like. Clearly, there's many, many ways how we can write a distribution like that. I already said that we can, every distribution can be written as a sequence of conditional distributions if we just choose the right things to. So in fact, here's two different factorizations of the same distribution. One is you start with x1 and then you condition on these three, then you put x2, conditioned on the remaining ones, 3 on the remaining one, and 4. This is completely equivalent. Every distribution that can be written that way can also be written that way. Right? That's what we saw in the beginning. We can also choose a slightly different order. We can put x3, condition it on 1, 2, 4, 4 condition on 1, 2, 1 on 2, 2. Again, this is a completely identical way of writing this thing. But they correspond to different models, I mean to different arrows and boxes, right? So here, x4 is conditioned on 1, 2, and 3. So that's not true. That's not true at all. Ah, of course it's true. Sorry, you should correct me. You look always for the parents, right? Sorry. So x1, so one term enters into the model that is x1 conditioned on all its parent. So this is a parent, and that is a parent. So you have a term x1 conditioned on its parent. Similar, this one has 2 parents, this one has 1 parent, so it corresponds to this distribution. Here you have slightly different arrows. Now x3 is conditioned on all 3, which is this term, and so on and so on. So you have a certain number of variables. How should you write them as a graphical model with arrows and so on? Well, that depends on how easy you can get it based on the conditional independences that you know. So we saw that for the Holmes examples, some things were independent of others conditioned on thirds, so that would make you need to condition on fewer things. That means you need fewer arrows. So the conditional independencies should tell you how you can write the model in the easiest possible way. And that means you save parameters in storing it. That means you save computation and so on. So clearly the structure that we get has something to do with what is independent of what, right? We need to write them as a product, but which parents we put into the product has to depend on, well, what it depends on, right? It's important to remember, or to note that it's not true that a variable is independent of everything that is not a parent. That is not true. So it's not that variables that are not your parents have no influence on you. So for example, let's look at this distribution, 1, 2, 3 variables. The model tells you that 1 is conditioned on nothing, so you have p of 1. 2 is conditioned on, that way, sorry. So this is a parent of 2, so 2 is conditioned on 3, and 3 is conditioned on 1. Right? So that is the graphical representation of this factorization. So clearly, let's see, 1 is not a parent of x2, right? But that does not mean that x2 is independent of x3 when we conditioned on x1, for example.
Is it true that if we drop the direction and we'll make non-directed graph, then the cluster of this graph will show us what's independent?
We haven't talked about undirected models yet. That comes next. But if stuff is completely separated from each other, with or without arrows, yes, then it's independent.
Just look at this directed graph, at least it was not directed.
Well, then you have to know how to do the undirected. But yes, if stuff is completely not touching nowhere, there's no path at all, yes, then we can, it will follow in a second that these are independent. But most things, actually almost everything we have are pretty much dependent, otherwise it's boring. So if you have really completely marginally independent stuff, typically you can treat it separately and you do not need to model it together. It's conditional dependence and independence that makes stuff sometimes tricky. So in this case, you have a conditional dependence that how x3 behaves depends not just on x1, but its distribution is also influenced whether you know x2 or not. So for example, the state of x3 and x2 could be coupled because some values of x2 are impossible if certain values of x3 arise. So the distribution of x3 does not depend just on the parents. That's something important to keep in mind. But that makes it tricky, right? Because that now what is completely independent? I mean, what is conditionally dependent and what is not? Which variables in the graph interact and which ones do not condition on others? So it's one of the questions in graphical models. Given a graph, which parts are conditioned from conditionally independent of each other, given some others? I'm talking too much, I think. Okay, a few more minutes. So, for example, this graph. Can somebody tell me what is independent of what? X3 and X4 are independent. Conditioned on what? No condition. Okay. That's possible, yes. Okay, let's start with a concrete question. Are X1 and X2 conditionally dependent if we know the state of X4? Why not? Maybe it is, maybe it's not. Who can tell? So, let's check. I did the math. You could have done that, right? Of course it is, but we haven't talked about the Markov Blanket. The Markov Blanket is 2 slides from now. Yes. Yes, it is. You should not be here. Okay, so are X1 and X2 conditionally dependent given X4? That is not a trivial statement. But of course we can do the math, right? I mean, we know that this distribution factorizes according to these factors. 1 depending on 4, 2 depending on 3 and 4, 3 depending on nothing, 4 depending on nothing. Now, we are interested in the conditional distribution of X1 and X2 given X4. Let's write it down. It's this guy. We do all the math. Stuff cancels out. For example, these two cancel out, etc. And what we end up with in the end is the probability of X1 given X4 multiplied with the conditional distribution of X2 given X4. And this is exactly the definition of conditional independence, right? The joint probability of these two given 4 is the product of one given 4 and the other given 4. So yes, these two, I mean, actually already just knowing this graph will tell you that X1 and X2 are independent given X4. So how about X1, X2 given X3? No such luck. So we can do the math, but there's nothing, I mean, it will not cancel out that way. It will not become a product of things. I think I didn't do the math. I just wrote no. So there's a few criterion how you can tell, and this is, if you actually work with directed graphical models, something to keep in mind. And it's going to be easier for undirected models soon, but for now, this is what we have to live with. So one of the main criterion is related to the concept of a collision. So you want to know if things are independent. Take a path from some A to some B, then a collider is a node in between which has 2 arrows pointing towards it. So this is the shortest possible example. You start at A, you move around your graph, you arrange at B. If at some point in between there is a variable C that has arrows coming in from both sides, that's called a collider. Okay? Just the names. So let's check these 3 graphs for colliders. Maybe you have already. So here's one of the graphs, X3 pointing these 2 ways. Is this a collider? No. No, it's not. Are these 2 independent if we know X3? Well, we can do the math. Turns out yes. Next graph, X, didn't we have that before? Actually I did the math. Oh, cool. So you do the math, you write this conditional, stuff cancels out, you end up with a product. So this and this is the same, you have conditional independence. That's a typical homework question, you're lucky. So next graph, 1 pointing to 3 pointing to 2. Is X3 a collider? No. Doesn't have 2 arrows coming in. Nope. Are these 2 independent? Yes. Again, you can do the math, and after some massaging terms, you end up with this decomposes into a product of 2 things. So, also worked out. This one, is X3 a collider? Yes, finally, we have 2 things pointing in. Are these independent? No, actually. So now if we try to do the same stuff doesn't cancel out. What we end up with is some conditional divided by the margin of 3, and there's no reason why this would be 1. So we have not achieved independence. So that's the general rule for these 3 variables. For 3 variables, 2 are conditionally independent given the third one if there is not a collider in between. If the third one in the middle is not a collider. Of course, 3 variables is not the most exciting case, but we see that colliders have to do something with independence, or conditional independence to be precise. Okay, now here's the more formal criterion. I can never remember it. And it's called D-separation. So think of 3 sets of random variables in your graph. Could be all of them split into 3 parts or just a subset. And there exists a general algorithm to check if these 2 sets of variables are independent of each other given the third one. And it's called the D-separation criterion. The D I had to look up. It stands for directional. It doesn't stand for, I don't know what else I come up with. So for every variable in the first set that you want to check, and for every in the second one that you check every path between them. Right? It's a directed graph. You can enumerate the paths between them. We call a path blocked if there is a node in between on the path such that either it is a collider and it's not in the set we condition on, and none of its descendants is in the set we condition on. So from everything you can continue to follow the arrows and see any descendants. So if it is a collider and it's not in the set that we condition on, then we call the path blocked. And also, if it's not a collider and it is in the set we condition on, then we also call the path, call it blocked. That's the technical conditions. If all paths between x and y are blocked by either this or this kind of w, then we call the 2 sets separated by z. And if they are separated by z, they will become conditionally independent by z. It's an algorithm. You can implement it. It's not particularly efficient because you have to enumerate all paths, but it's doable if your model is not, we're not talking about thousands of variables, right? We're talking a handful. It's not the most intuitive to memorize for an exam. So there's other things you can do. One special case that is quite useful is the so-called Markov blanket that you already asked about. So if you're interested in some kind of A, like this node here, or a set of nodes there, and you want to know if it's, what is the smallest amount of others that you need to condition on such that all the others are irrelevant, then this is the so-called Markov blanket. So the Markov blanket is you need to condition on all parents, on all children, and on all parents of children. So this is the modern world where children have multiple parents, and it's not always yourself, but it can be other people. Right? So if you're interested in A, you have to look at the parents, you have to look at the children, and you have to look at the parents of the children. If you condition on all of these, the other ones will not matter anymore. So A is conditionally dependent of the outer ones conditioned on this set. And that's called the Markov blanket. There's another way, and that's maybe the last one to say. Another way of checking conditional independence between things is what you suggested. You go from a directed to an undirected graph. And for undirected graphs, things are easier. So we haven't talked about undirected graphs, but this method doesn't really need it yet. So you can also check if 2 parts of the model are independent of the others by the following 3 steps. First, you build a so-called ancestral graph. That means you remove all nodes that are not of your current interest and that are not ancestors of your current interest. So everything that is far away and doesn't really, correspond to what you care about, you can already discard, including all edges. So you just shrink the graph to only care the stuff that is relevant to you. Then you do a step that beautifully was called moralization. Somebody came up with that. So apparently it's immoral to be a parent, to be a child with 2 parents that are not married. So what do you do when you have something immoral? You moralize it. So when you have a child with 2 parents, then you make the connections, you connect the parents. Afterwards, you can remove all the directions from the arrows. So you go from a directed to an undirected graph. And finally, you have an easier criterion. So you just remove Z, which you want to condition on, and the links that connect you to Z, and then you check if there's still any paths left from X to Y. If there's no more paths, if the stuff is 2 joint components, then they were conditionally independent. Again, something you can implement if you care about this kind of reading it off automatically. Otherwise, well. Okay. Yeah, why not? That brings us to the question of which models specify the same independence relations and which one do not, right? Which is called Markov equivalence. So we call two graphs of this kind Markov equivalent if they specify exactly the same kind of conditional dependence statements, and otherwise we don't call them Markov equivalent. So this is a definition that works for directed and undirected. The undirected comes next, but for directed, we can already look at some examples. So one word that is useful to know is the skeleton. So the skeleton is what you get out of the directed graph when we remove the arrows, as we did in the previous step. Immorality already mentioned. So if a child has two parents that are not connected to each other, we call that an immorality, or people call it that. So Markov equivalence is easy to check. It's a graph that has the same skeleton and the same set of immoralities. So this is not a way of telling what is independent of what, but it's a way of checking for two graphs if they have the same independencies. Right? So remove the edges, check if all the edges afterwards are the same, and also the connections between parents are the same. 4 examples. All of these have 4 nodes and 2 arrows. All of them have the same skeleton. Right? If we ignore the directions, these are all the same. A, B, and C have no immoralities. So this doesn't have 2 parents. I mean, nobody has 2 parents. This has only 1 parent. This one has only 1 parent. This one has 2 parents, and they don't have an edge between them. So this one has an immorality. These ones do not. And by the criterion means this guy is not equivalent to these 3 in terms of the conditional dependencies. And we already saw that, right? We saw that this one had this weird collision, whereas these ones do not. That was all about conditional dependencies and how you read them off from graphical models. It's not the most intuitive thing. Let's have another short break for me to drink, and then we talk about undirected graphs afterwards. Thank you.